Hi, welcome to another edition of Calculus 2. Today we are going to talk about partial fraction decomposition. Let's go and see how we handle this very useful topic. Okay, partial fraction decomposition is something that you essentially start doing since elementary school. It might come as a surprise, but here's one of the fractions. This is one of your favorite, 22/7. Well, you can divide the numerator by denominator, and then you have a quotient of 3, remainder of 1, and then you can write 22/7 as 3 plus 1/7. That's an easy, simple partial fraction decomposition. Let's go to another one, a little bit more sophisticated. 1/6. How can I write it as a sum or difference of fractions? Hopefully simpler, smaller fractions. Well, you can easily convince yourself that 1/6 is 1/2 minus 1/3. You notice that these have to be factors of that for the equation to work. Well, what we have in mind in algebra is the situations where there's a polynomial in the numerator and a polynomial in the denominator, and we want to break it up. So here's an easy example: 2 over x squared minus 1. The question is, can you give me two fractions such that if I say add or subtract them, I get this? So the idea is you're doing something opposite of taking common denominator and adding things up. You're just breaking a fraction to its pieces. Well, looking at this, what kind of a denominators do you suspect I could have on the right hand side? What do you think can be on the right hand side? So just take a minute and try to perhaps guess your answer. Guess your way to the answer, or perhaps you have seen it in calculus already, calculus 1, or maybe even high school. So what are the fractions that we have here? Let's go back. So obviously the denominators that I have on the right hand side have to be factors of the denominator on the left hand side. So this one breaks to x minus 1 and then x plus 1. So maybe you can think about it, how come I cannot have, say, x plus 2 or x minus 3 and such? But if this is our starting guess that our denominators are these, what do you think the numerator should be? Well, I look at this side and say, well, there's no x here, so whatever numbers I have here, they have to, after they multiply x, they should cancel each other out. So again, perhaps you want to continue guessing and telling me what should I put in the numerator of these fractions. So we said they have to cancel each other out, so let's start with the easiest number we can think about, 1 and minus 1. Well, my x's cancel now. Let's go actually see. When you take a common denominator, what do you have? X minus 1 and x plus 1. In the 1 times this will be x plus 1. Minus 1 times that will be minus x minus 1. And of course now the x's do cancel. 1 minus minus 1 is actually 2. We are back to what we had started on this side. So in this case we could easily guess our way to the answer. Sometimes it's not as straightforward. So here's a rather nasty example. So suppose I have 1 over x plus 1 cubed times x squared plus 1. Now I gave us a little bit of a reprieve here by actually factoring the denominator, so that step of the problem is made easy for us. The question is, what can you expect on the right hand side? Well, we are going to learn today how to go after this. It turns out in the right hand side I have what do you think I can have on the right hand side? What kind of fractions show up? Well, we look at this factor, x plus 1 cubed. And on the right hand side, I could have just x plus 1 or x plus 1 squared or x plus 1 cubed. So any of these things could have been here. Now I don't know how much of each of them would be needed, but it's possible that all of them are showing up on the right hand side. Well, this one should come from something on the right hand side as well. Obviously it doesn't come from these. I hope you don't confuse this one with this factor here. This is called irreducible quadratic, something that cannot be factored into ordinary real numbers. So this one is going to be in this case we have power 1 here, and here we also have power 1. The numerator of this kind of fractions, however, is going to be a linear expression. So here I can have any number, here I can have any number, here I can have any number. Here I expect a linear expression. Lord, let me ask you, why would you convince yourself that there shouldn't be any x squared here? But we'll come back to that issue later on. The issue of partial fraction decomposition is to figure out a, b, c, d, and e such that if I add all of these, it becomes that. So how do we go about the denominators? Any of these linear factors that I have, starting from power 1 to maximum power that I have here, I should write all of them. And if I have this so-called irreducible quadratic, meaning things that cannot be factored into that kind of expression, then I write them also from power 1 to the maximum power I might have on this side. The numerator of these things, however, are going to be linear expression, meaning some multiple of x and just some number, no powers or anything here. The objective is to figure out what a, b, c, d, and e are going to be. Typically the problems are rather lengthy in terms of algebra to do. Most of the examples that you are going to see will be of this nature, so that it can be easily quickly carried out, but in principle it can be lengthy. So in this example, let me just go ahead and give what the answer turns out to be, just so that we are completing this process. A turns out to be 1/4 and b turns out to be 1/2, and then this is x plus 1 squared, and c turns out to be again 1/2. This 1 over x plus 1 cubed, and d and e, both of them turn out to be minus 1/4, so minus 1/4 of this turns out to be x plus 1 over x plus 1 x squared plus 1. Okay, so we have a few things ahead of us. First of all, how do you find a, b, c, d, e? We are going to give a general method and then also occasional shortcuts. And the other thing perhaps everybody is thinking about that is, well, what are we going to do with this thing? Interesting mathematical problem perhaps, but what are the uses of this thing? So let me just mention a few words about the uses of this before we get bogged down with all the algebra. Hopefully that makes it a bit more tolerable. So in terms of uses of this thing, first time you are going to see this thing is going to be in ordinary differential equations. That's probably a course that you planning to take next semester, or maybe you're taking it now, and we are going to study waves in that course. When we want to study waves, we are going to come across a topic called Laplace transform, and partial fraction decomposition is going to be a main tool for us to figure out what happens to these waves we are discussing. Those of you headed toward the electrical engineering circuits and such, you're going to see exact same thing. they like the letter S in that Laplace transform there, but it's pretty much same as what we are doing. And then the function they look at, very similar to what we are looking at here, is called the transfer function. And one of the main tools that they are going to use at that time is the partial fraction decomposition. So here, let me give a short proof of you to you. This is a lecture given by Dr. Berry in Rose-Hulman Institute, and it's talking about partial fraction expansion. And as you see, it's in the course on circuits and systems. So maybe a couple of semesters away from where we are right now, but the issue is going to come back then. So it does have applications, but we cannot get into that detail right now. You're going to get there in the future. So let's go ahead and start with some basic examples on this topic, and then we are going to come to some extended questions. Let's start with a simple example. So suppose we say find partial fraction decomposition. So I'm going to abbreviate it for, let's say, x over, let's start x plus 3 over x squared minus 6x plus 5. So I want to break up this fraction. Well, the idea itself makes sense, because if you have a complicated expression, why not break it up so that whatever you want to do to it will be easier for you to do. So that's the main idea. This might look like complicated. Perhaps if we break it down, it'll be easier for us to handle. Well, what is it that we have in mind in this course? We want to take an integral. Taking integral of this thing straight as it is, it's going to be a bit complicated with those trig substitutions and stuff. But if we go after partial fraction decomposition, the expressions we are going to look at are going to be much smaller, and we have a much better chance of integrating them right off the bat. So here we go ahead and say, well, what is the factorization of the denominator? So here's a basic idea from your algebra class. That means back in middle school. How do you factor this expression? Well, this is an easy one. You're looking for two numbers such that the product is 5, sums to minus 6. So typically these problems are friendly when it comes to factorization. So we have the factorization. So that is what we suspect will be in the denominators. There were such things that when they were added up, that was created as the common denominator. But how about the numerator? What are those? Well, we don't know what they are. So we call them A and B for a moment, and then we try to find them. So these are parameters to be found. Well, how do we find them? Several ways. One standard method of doing this, and another one which is going to be a bit of a shortcut that is sometimes applicable. Well, what's the standard way? Standard way is just put these things back together. Just take a common denominator and add them. So x minus 1, x minus 5, and then numerator times this denominator, a times x minus 5, and b times x minus 1. But the denominator is obviously the same thing. What we need is the numerators to be identical to each other. So what I want to do is to make sure x plus 3 becomes same as a times x minus 5 plus b times x minus 1. What should be the value of a and b such that the two sides are identical for all values of x? You're not solving this as an equation. We are solving this as an identity. This has to be same as that. Okay, standard way of doing this goes like this. If two polynomials want to be identical to each other, then after you arrange them in terms of powers of x, their coefficients have to be the same. Meaning what? meaning go ahead and collect this thing. So I go to right, so x, what are the factors of x? A and b. And then what's left? What is left is minus 5a and then minus b. So now we say this polynomial is identical to that polynomial if the coefficient of respective powers are the same. That's the only way two polynomials that have been simplified can be equal to each other. So what we have now, a standard way, says a plus b has to be 1. The missing coefficient, of course, is just 1. Minus 5a minus b has to be 3. So we always end up with a so-called system, set of a linear system of equations to solve. These are typically easy to do to solve, and there are actually courses on that kind of stuff. But how do you handle it? Well, you have learned a variety of ways in high school: elimination, substitution, Kramer rule, or whatever you like. Here is very simple. I can add these two equations to each other. On the left hand side I get minus 4a, b's cancel. On the right hand side I got 4, and I get lucky here that my a becomes an easy number. Well, if a is minus 1, you can go plug it in any of these equations and figure out what the b is going to be. So a being minus 1, it tells me that b has to be 2. The work that we want to do is goes well beyond just figuring out an a and b. We have a lot of other things to do, so it's better to double check at this stage to make sure we are not making any kind of a mistake, because we have to recover quite a bit if we want to come back and do this thing. So we go ahead and double check the second equation. Do these satisfy the other equation? Well, minus 5a is going to be plus 5, minus b makes 3, and that is 3. So it looks like we are on the right path. So I have my a and b. So in this approach we got that my solution is minus 1 over x minus 1, and then b turned out to be 2 over x minus 5. So that was easy. So the standard way to find an a, b is that you go ahead and add up all of your fraction. You simplify your numerator, equate it to the left hand side numerator, and the respective coefficients have to be the same. You have a linear system, you solve it, verify it, and then you have your pieces, and then you can go ahead and do whatever you wanted to do with this thing. What about a shortcut? Sometimes you can apply a shortcut. Let's go back here and I write that equation again. I have x plus 3 is equal to a times x minus 5 plus b times x minus 1. So now I try to eliminate presence of either a and b by a judicious choice of x. What do you mean judicious choice? For example, if I choose x equal to 1, well, this becomes 0, b is gone, and a is the last man standing. I can figure out a. So I go ahead, set this coefficient equal to 0, figure out what x is going to be, take that x and plug it on both sides. So this becomes 4 is equal to a. Let me write it out what happened. So x was 1, so 1 plus 3, a times 1 minus 5. So say 4 is equal to a times minus 4. So of course a has to be minus 1 for this thing to work. The second time around, I come and try to get rid of a. I say, okay, to get rid of presence of a, set x equal to 5. And then this factor is going to go. When x is equal to 5, then I'll have 5. Let me write it. 5 plus 3 is equal to, on the other side, I'm just left with the b terms. So it's going to be 5 minus 1. So this tells me 8 is equal to b times 4. So that tells me b must be 2, which is what we got before, thankfully. Another way of arriving at that. Okay, now that's the general idea. This was a simple example. Bigger example is essentially the same thing. What are you going to do with this thing? So well, right now all you're going to do with this is integration, but as we said, in the future you have waves to analyze and circuits to analyze and so on. So right now our homework type of homework problems that we are going to see is something like this. Find out what is let me see what was we have here. X plus 3 over x squared minus 6x plus 5 dx. That is what we had over there. Okay, how do we do this? Of course we have those other methods, but this perhaps is the easiest one. Instead of the trig substitutions and such, and we can go and just write the expression that I have, minus 1 over x minus 1 plus 2 over x minus 5 dx, minus 1 and 2. Well, these are basic integrals you see back in calculus 1. Integral of this one minus logarithm of x minus 1, and this one is 2 logarithm of x minus 5, and then you throw in a constant for good measure. If you want to modify this thing a little bit just to see as a matter of practice, minus logarithm of x minus 1, where does this 2 go? Okay, quick practice from pre-calculus. If I want to rewrite this thing and move the 2 inside, where does the 2 go? Of course it goes to exponent of this expression. And then if you have 2 logarithm, one is added, one is subtracted, how can you rewrite it in another expression? Another question from pre-calculus. Do you remember the rules of logarithm? So what do we do here? Of course, a logarithm of ratio. The item that's added is your numerator. The item that's subtracted is your denominator. And then we have a constant. So of course this logarithm is separate, the constant's outside. So that's the logarithm here. Of course when you have a square you can do away with the absolute value, but if it was 3 you keep the absolute value. So that was a simple example of integration by partial fraction decomposition. Let me do another example. This one that I want to do is going to remind us of that very first thing from way back when. If you have a so-called improper fraction, you can get the quotient out and then you have a fraction like this. Sometimes something like that shows up in our integration problems as well. So here's another example. Suppose I have 2x cubed minus 4x squared minus 15x plus 5 over x squared minus 2x minus 8 dx. Okay, this looks like horribly complicated, but in fact it's a very easy problem. What is the very first thing we should do? Again, take your cue from that 22/7 problem that we were just looking at. What should I do very first step to make this problem manageable? Very first step, what do I do? So push yourself to do this thing. We come back. Well, just like elementary school, actually divide. Well, this division is called long division, or perhaps some other terminology for it. Divide so that your fraction looks easier. 2x cubed minus 4x squared minus 15x plus 5. Well, divide with denominators x squared minus 2x minus 8. How do you divide these things? Very easy, actually. Very easy, very easy. So you divide the leading terms, 2x cubed over x squared. What's the ratio? Well, it's obviously 2x. That's your quotient. Multiply back, you get 2x cubed minus 4x squared minus 16x. Take this thing and subtract from that to make sure you don't make a mistake. Maybe flip the signs and add to avoid sign mistakes. Well, these two have to cancel. We just designed it that way. Here, by coincidence and accident, this thing cancels out. Makes our problem a bit easier. And then this one, when you add them, you get just x, and you bring the next term plus 5. This is the remainder because its power is less than the power here. So what did we get now? The quotient is 2x. The remainder is x plus 5. Denominator is x squared minus 2x minus 8. And this whole thing is going to be integrated. Well, this is looking a lot easier than that one did. This looked scary, but now integral of 2x, well, x squared. Integral of that, well, exactly like the previous problem. You take this, do a partial fraction decomposition, break it up into pieces just like what we did here, and then what? And then well, you do the integration. You're going to have two logarithms, and then you're all done. Can I trust it that you are going to do this thing by yourself, and you're not going to need me to take this thing to the final step of it. Okay, so and this is for you to complete. So complete this thing as complete this thing. Okay, so what's the idea of a partial fraction decomposition? We have always a so-called rational function. Rational function means what? Means a polynomial divided by some other polynomial. These are almost all time. Real polynomials, meaning all entries are just real numbers. Numerator is some polynomial, denominator another polynomial, and in a single variable. And then we want to play with these things. Let me make the discussion specific so that it doesn't sound too abstract. Suppose the polynomial in the denominator is factored for us. So that's a big obstacle by itself, and many of the problems that you see, these are either easy to factor or they're actually factored for you. So let me take a problem where things are factored. Suppose I have a factor of x plus 2 cubed and another factor of x plus 5, say to power of 4, another factor of x squared plus 3 to power of 2, another factor of x squared plus 10 to power of 3. Now I'm making a big job for myself, and say numerator is some let me not make it specific, is polynomial, for example, x to power of 10 plus x to power of 7 minus 20x, and so on. So something. How do you do partial fraction decomposition for this? Step 1, you check the degree of this. If the degree of this is equal or more than the degree of denominator, you carry out a long division, just like what we did here. So if you can divide, then you should divide so that the problem becomes easy. So what is the telltale sign? If the degree here is 2, 3, 4 or 5 or whatever, more than 2 or more, then it makes perfect sense to actually divide and separate your quotient. So step 1, so we write here step 1, so let me call this polynomial by some name. So let's call it this common polynomial, call it say p of x. If degree of p of x is larger than or equal to what? Let me see if I can ask you, at what point is it that you have to do that long division? Well, we said if it is greater than or equal to the degree of denominator, you have to do the division. So what's the degree of the denominator? So it's another question. Degree of denominator. Well, the degree of denominator, let me pause for a second and ask you, what is the degree of denominator? Do you see it right away? What is the degree of denominator? Well, degree 3 here, add a 4 to it, so by now it's 7. So I have an x cubed here and I have x to the power of 4 here. So far I have 7. What do I have here? Do you see that if you have x squared and square it, now you get a 4? If you have x squared and cube it, by now you have a 6. So this denominator degree is 17. Of course, you never dealt with the polynomial of degree 17, but we're just talking in general. If the degree of numerator is larger than or equal to degree of denominator, then do a long division. So if you do the long division, just like this problem, you're going to have a quotient. So this is called the quotient. And then this one is called the remainder. So you do that one first. The quotient is going to be a polynomial, which is going to be easy to integrate. And then the issue is, well, what do I do with that remainder divided by this denominator? Then comes the hard part. The hard part is, well, what could be in your denominators? Well, let me make a lot of space because I need a lot of space. X plus 2 cubed comes from either you have x plus 2, or you have x plus 2 squared, or you have x plus 2 cubed. So from degree 1 to maximum degree that you have here, you have to make room for that. How about this one? Let me write that in a separate line so that things don't run into each other. X plus 5 to the power of 4. So either you had x plus 5, or you had x plus 5 squared, or you had x plus 5 cubed, and then you had say x plus 5 to the power of 4. Any of these things could have been there, resulting in this kind of common denominator. Well, what should be in their numerators? Well, we don't know, some number, a, b, c. I'm afraid I'm going to run out of letters of alphabet. A, B, C. What's after C? C, D, E, F, and G. Okay, how about these? Well, you have x squared plus 3 to the power of 1, and then you have x squared plus 3 to the power of 2. Any of them could be. So who's supposed to be in the numerator of these things? So G, H, I, J, K. So now HX plus I, JX plus K. So each of these things give birth to 2 unknown coefficients to be found, these 2 numbers. How about that one? Well, I made my job too hard for myself. Let's just do that so that for finale we have this one. We have x squared plus 10 to the power of 1, x squared plus 10 to the power of 2, and what else? x squared plus 10 to power of 3. And how about their numerators? As k, l, m, n, o, p, q, so this is just a number. Okay, so that's how you write the partial fraction decomposition. Then you have to add all these things up, make an equation, and figure out all the unknown coefficients all the way from a to q. Of course, that's easier said than done, but we're just telling what is the principal idea, what is it that in general has to be done. Problem of that type is always delegated. If it was something this extensive, it's always delegated to a computer, but when you're doing by hand, it's 2, 3, at most 3 factors for you to deal with, and then you're all done. So let's go back. Step 1, if the degree of polynomial in the numerator is larger than the denominator, you do a long division. And then step 2, all the linear factors from degree from exponent 1 to the maximum exponent. What you write is all linear factors from exponent 1 to maximum exponent. Numerator of all of these things is just a number, an unknown number. Then if you have these kind of expressions, these are called irreducible quadratic, because you cannot break them apart like into those. Step 3, for all irreducible quadratics, again same, from exponent 1 to the maximum exponent that you see, and then numerator is a linear expression. No powers or anything in that one. So you see these blue ones, numerator is always like that mx plus p that you had seen in high school. Variety of those. For each of these things you have to have another m and another b and so on. And then of course the hard part is to, after all of these things, what are all these numbers to make the two sides equal to each other. Okay, let's just finish this lecture at this stage. It's essentially something that to be learned by lots of practice and problem solving. Now at the very end, what happens? At the very end, well, we are integrating. Integral of these things is straightforward. You have seen a lot of these in calculus 1. So integral of this first one is just logarithm. Integral of each one of these things, the exponent is going to be reduced by 1 and such. How about the integral of these? So let's go ahead, do a simple example of integration for an expression with irreducible quadratic. So suppose the question was, so after all of these things said and done, you still have to do an integral. So the problem can become lengthy. Suppose I have the problem of what is dx over x squared plus 1 squared. So something like this. How would I integrate that? Well, x and that expression, you can see that very easily, that if you do a u sub u equal to your denominator, then you are quickly done. The harder part is that constant there. If you have a constant divided by irreducible quadratic to some power, what would I get? Well, That is where our trig substitution is going to come back into play. So I go ahead and make that picture. So you remember, if this is x and this is 1, of course our hypotenuse is, well, square root of x squared plus 1. So idea that here is to use a substitution. X is equal to tangent of theta, and of course that means dx is going to be secant square of theta d theta, and radical x squared plus 1, that's hypotenuse. You notice that is just secant of theta. So if I want x squared plus 1, that for of course is secant square of theta. Okay, once we have our picture and a list of characters here, we can go back and see what happens. So our dx is secant square of theta d theta. X squared plus 1, that's secant squared, but then it has to be squared again, so it becomes secant to power of 4. Well, this becomes d theta over secant square of theta. Well, what is 1 over secant squared? 1 over secant is, of course, basic trig. 1 over secant is what? What is 1 over secant? What do you write it as? Quickly. Secant. Reciprocal is, of course, just cosine. So I have now come back to cosine square of theta d theta. Well, how did we handle that? You remember the double angle identities, or another method of your interest. So it would be 1 plus cosine of 2 theta over 2. That's the double angle identity, gets to be used quite often. Then what? Antiderivative of 1/2, well, it's just theta over 2. Antiderivative of cosine of 2 theta is sine of 2 theta divided by 2, and another 2 makes a 4, and then a constant. Well, I theta over 2 nicely sits there. Sine of 2 theta, I can write it as, we had seen this thing just a few minutes ago, sine theta cosine theta over 4. Then we have theta over 2 plus 1/2 of sine of theta cosine theta plus c. Okay, we are ready to finish this job. First of all, what is theta? Theta is, of course, tangent inverse of x. So that's step 1. So we just write this. 1/2 of tan inverse of x plus 1/2 of sine theta. Who is sine theta? Let's go write sine theta. Sine theta opposite to hypotenuse. That's my sine theta. So x opposite over, who is cosine theta? Cosine theta, of course, adjacent to hypotenuse. So I write that's 1 over radical x squared plus 1, and a constant. I might as well put my 1/2 out. Tan inverse x times 1, radical times radical, and then a constant. So what is this? Let's just remember what we did. We started with dx over 1 plus x squared squared. That's that integral. So these type of integrals can be done with trig substitutions. Of course, there are some of them. Sometimes they're going to take a while longer. So all of these are going to be done by trig substitution. There are other methods available too, but that's what we have learned so far. These, we said, these are straightforward. They just lose the power and you have to adjust the coefficients. These are going to give you logarithm, as you have seen in calculus 1. Okay, so I will be having some homework related to this, and hopefully you all get it done quickly and easily. Until next time, good luck and God bless.